Thank you all for coming. So my name is Arun Majumdar. I'm the Dean of the Doerr School of Sustainability, and I want to welcome you all for the Dean's Lecture Series of the Doerr School. The purpose of the Dean's Lecture Series is to create a discourse and identify opportunities to learn about those issues that don't fit neatly into departments or units, but span the gamut of scholarship, research, education, and all the things we do. And the goal is to identify those topics where this knowledge and scholarship and the solutions are critically important for our vision of humanity and our planet thriving together. The first set of lectures that happened in the autumn quarter and the winter quarter focused on environmental justice. We needed to learn more about this. Today's lecture is focused on data. I've said this in the past that data science is the algebra of the future. But the future is here. Data is critically important in many, many aspects of sustainability. What happens in energy, climate, water, food, biodiversity, ecology, global health, they're all interrelated. And data is going to be critically important, not only for the science and the engineering, but the social sciences, the decision-making, the journalism, the policy-making, all of it will require some elements of data. And if you group them all together, it is how humanity on a planet, again, thrives together. We will need data to focus on that. Today's lecture will feature 3 speakers in a coordinated talk about a new system for organizing and making data from multiple sources easily accessible and useful, and it is powered by Google's Data Commons. To introduce the speakers and to moderate the panel thereafter, I would like to invite Jim Leap. Jim is the William and Eva Price Senior Fellow in the Stanford Woods Institute for the Environment. He also serves as the co-director of the Center for Oceans Solutions. Jim has more than 3 decades of conservation experience, spanning a broad range of conservation issues on every continent. From 2005 to 2014, he served as the Director General of the World Wildlife Foundation International and leader of the Global World Wildlife Foundation Network, which is one of the world's largest conservation organizations active in more than 100 countries. Before going to WWF International, Jim directed the conservation science and initiatives of the David and Lucille Packard Foundation. I had the honor to travel with Jim, and this was my first time this year to visit Davos. And it's just an amazing experience because if I had not gone with Jim, I would not have known anyone. Jim knows everyone out there, and everyone knows Jim. So thank you, Jim, for introducing me to Davos. But with that, let me invite Jim.
Doesn't matter order. So thank you, Arun, for that introduction. I think it's fair to say that life in the new school is a string of mind-blowing opportunities, and this is certainly one of them. The idea of a Stanford Data Commons is an idea that Arun came to many, many months ago and has been the product of many Sunday mornings in the Google offices with Arun and Guha putting their heads together about what could happen here. But all of you can imagine the possibilities. If you take the extraordinary and fast-growing data capabilities of datacommons.org, the Google engine, and you combine that with the extraordinary and rapidly growing data and analytical outputs of this school, there's just a lot we can do to bring information to bear on solving some of the most stubborn problems. I spent a lot of time on oceans. In oceans, we've seen an explosion of data over the last decade from satellites, from sensors in the water, from many other sources. If we can tap those data and translate it into information that allows coastal communities and coastal nations to manage what's coming, ocean heat waves, harmful algal blooms, other stresses, we will make a big difference in what happens in those communities and in those countries. And that's just one example. We're going to start here, not surprisingly, with energy and climate, which has been first out of the blocks in exploring the potential. And we have a pretty amazing panel to do that. So we start with Ramanathan Guha, who is the founder and leader of datacommons.org. I think for many in this group, the most important thing is that he got his PhD here in 1992 with John McCarthy. So one of the pioneers of artificial intelligence, and I gather the person who called it first artificial intelligence, but since then has worked for many of the most important tech companies and has a history of developing tools, standards that are of broad utility across the sector. And Data Commons, of course, is probably the single most, well, it's certainly the most recent and one of the most important of those. He's a vice president at Google. I'm told that even more important, he's a Google fellow. And that's the license with which he has developed this work. From the Stanford side, we have Ram Rajagopal, who is an associate professor of civil and environmental engineering. Got his PhD across the bay at Berkeley in electrical engineering and computer science. Ram spends a lot of time understanding data systems and how we drive the changes that have to happen in those data systems, how we integrate renewable energy, how we build systems that have the resilience that we need, how we understand patterns of demand. He has 30 patents, maybe more, which is 30 more than I have, but has really been a leader in this field. And then finally, Aditi Shashwati, who is assistant professor of environmental systems science here at Stanford. Aditi understands the atmosphere. She models atmospheric and ocean processes and circulation to help us understand the dynamics of those systems. She was, before she came here in 2018, she was a junior fellow at the Simons Foundation in New York. She was a postdoc at Columbia. She got her PhD at MIT. So, got a lot of horsepower on the other part of this stage. And they're going to take us into this with one integrated presentation. When they finish, we will have a chance for a bit of a discussion within the panel, I hope, and then some time for questions from all of you. So please don't be shy. Store up your questions, because there's a lot to explore here, and this is at least a chance to get started. So with that, we turn it over to Guha to take us into Data Commons.
Thank you, Aaron. Thank you, Jim. Thank you all for having me here. So this has been the labor of love for 6 years, and some of my team is standing there. So if you have any compliments, this compliment should go to them. But let me get started. To set the context, there's a lot of data out there, from the IPCC, census, RBI, BLS, BEA, USD, and the list goes on and on and on. This data is essential for everything, for science, journalism, policy, and even our end users. Unfortunately, using this data is incredibly painful. It involves repeated data wrangling that is expensive and error-prone. I want to motivate it with a single example. If you want to ask which California counties are most at risk from climate change in the next decade, imagine you want to answer this. So we know, and Aditi will go into some of the math, that sometime in the next 10 years, the peak temperatures in Inyo and Imperial counties are, with a 5% likelihood, likely to cross 50 degrees centigrade, maybe just for a day or so. And when the temperatures reach such extremes, we have all kinds of risks. So we want to understand what's going to happen to food, health, shelter, jobs, etc. in these counties so that we can prepare. To do that, you need data from, of course, all the climate stuff, IPCC, NOAA, and so on, about health stuff from CDC, about disasters from HERDAT, demographics from census, education, wages, BES, BLS, NREL, list goes on and on and on. But the key point is that in order to address climate change, we need data not just about the climate, but also about all these other things, about health, food, farming, water, employment, and so on. And these are incredibly messy data ecosystems. The people who are making the policy, whether it be in Washington or Sacramento or in these counties, cannot be expected to do all the wrangling in order to figure out who is most at risk and what needs to happen. Somebody needs to organize this data, and make it easily accessible, which, as you guess, is what Google does. And that's what Data Commons mission is. Taking it one step further, after we have done this, and not just for end users, but for researchers, policy folks, administrators, application developers, everybody should be able to use this. And for that, this has to be done in an open fashion. It's got to be open source. And to the extent possible, it's got to be open data. And most importantly, it's got to be an open process. No black boxes saying, trust me, this is what it is. Everything needs to be essentially of a quality which can be peer reviewed. So our approach, there's no magic, there's no silver bullet, there's no magic potion here, is let's do the data wrangling once and for all and just share it with everybody so that it doesn't need to be done over and over and over again. So we take a very large number of different data sets from all of these and many, many, many more sources, and the list goes on expanding. And we do all the wrangling, meaning we clean the data, we build open schemas on top of schema.org, we align references to entities and attributes and all of that stuff, and build this giant database. It's called a knowledge graph. The details there don't matter. It's too big for most people to download. It's several petabytes. If you want, you can download it. And so we provide APIs on top of which many different applications can be built. There's an analogy here to satellite imagery. In the late 90s, NASA had its Landsat imagery up on its website. If you wanted to, you could figure out what your house looked like from the sky. You needed the latitude and longitude of your house to the third decimal place. You downloaded a set of tiles. You went to this different site, got a Java applet to stitch these tiles together, used a different mechanism for sharing these, and so on. So in theory, it was available. In practice, very few people did it. What Google Maps really did was it did all this data wrangling once and for all and gave it to people in a very simple-to-use package, and that literally changed the way we look at the world around us. That's what we're doing now. So if you want to ask that question, which California counties are most at risk from climate change, instead of searching for data sets, cleaning, joining, etc., you should be in a world where we can just ask in natural language. So concretely, what have we built? There's the code, open source, cloud-based infrastructure for storing, serving, et cetera, these big knowledge graphs. There's, importantly, an open process for curation on GitHub, open standards for these schemas. There's one really important point. What we're creating is an ecosystem like the web. The idea is not to take all this data and put it in one place, one ring to bind them all at Google. No, it's more like the web. There are many websites. All these websites are each is controlled by its own organization, but they all use the same schema, HTML and JavaScript and CSS and so on, and they answer the same API, HTTP. Same model here. Many different data commons from different organizations, different topics, different access controls. All the data commons tools work on all of them. On the web, the deal is you put up a web page, you can suddenly link to other web pages, and other pages can link to you. The analog of that is it's easy to join data from across different data commons. We already have a number of partners, as you can see some of the logos, and today we're really excited that Stanford is finally going to join the ecosystem. So one question is, what's the carrot? Why should somebody put up a data commons, right? And I want to motivate this with a particular example of Feeding America. Feeding America is the second biggest charitable organization in this country. It runs over half the food pantries in this country. It's kind of behind Second Harvest and behind many of these other things. Over the years, they have come up with an index called the Meal Gap Index, which is a measure of food insecurity across different counties. What they really would like to do is to understand the correlation between food insecurity and many other things like cardiac health and education and drug use and housing and so on. Unfortunately, this data, as we saw in the earlier diagram, is just distributed all over the place. And it's simply beyond the skills or capabilities of Feeding America to pull all of this data together. The Data Commons contract is, if Feeding America makes its meal gap data available in a data commons, and this other data is available in a data commons, then doing this analysis should be simple. That's the real catch. There have been so many proposals over the last few decades where everybody, if everybody were to share their data in a common format, common schema, so that it could all be joined together, wouldn't it be a wonderful thing? But you have a jumpstart problem. And Google decided to solve this jumpstart problem by saying, we are going to bite the bullet. We are going to take the century or so it's going to take all of these important data sets together and build this base thing so that when Feeding America or someone else brings in its data set, it has a rich base that it can join against. In fact, 80–90% of our work over the last 5 years has gone into that. There's a base layer, people, places, economy, demographics, economics, housing, crime, education, from all of these and many, many, many other sources. One of our crown jewels is the Sustainability Data Commons, climate models, energy, disasters, emissions, water, agriculture, food, hunger, and the list goes on. So how big is this? It's about 3.5 billion time series, and the best way to explain this is in comparison to something like the FRED. The FRED is the St. Louis Federal Reserve's econometric database, which is sort of the basis that is used by the US Fed and most of the Federal Reserves across the world to make their monetary decisions. This is about 4 times that size. There's also the same kind of philosophy applies to many, many areas. As a biomedical data commons, in biomedicine, again, you have this kind of siloization, and actually that one was built starting at Stanford by Sam Pigos, who's now at ISB in Seattle. And if there's time, I can tell you a little bit about that. Accessing the data, there's a programmatic API, of course, what you would expect. There's a suite of visualization tools. Let me actually walk you through a couple of those visualization tools. So this is a map visualization tool, which is viewing things at the level of US states. These are CO2 emissions from across different states in the US. Those dots are the major emitting sources, mostly petrochemical refineries. It's interesting to see how much Texas puts out. It's also these numbers in these over here, in parentheses here, are the number of variables that are available at a US state level under each of these categories. That gives you an idea of the size of this piece. So for example, if you look at demographics, these are all the variables, and you can go drill down and down and down. The data is, of course, not just about the US. In different places, the data comes from different sources. The first one came from EPA. This one comes from Climate Trace. And it's fascinating to know that Texas puts out more CO2 than any other country across South America. Texas is a really fascinating place. Then there's a natural language interface in Google, and I'll be adventurous and try this as live demo. You can go do energy use per capita in India. That top result comes from Data Commons. Or fertility rate in Bangladesh. That top result again from Data Commons. Or something like life expectancy in Cambodia. It's interesting how data speaks to you. That dip there is the Khmer Rouge. Or number of women PhDs in Mountain View. Something very local. Or number of poor Hispanic women in Santa Clara County. And you can click on the more here and go to one of our dashboards. Here is a dashboard about Santa Clara County. There's things like this for every zip code, every state, every county, every city in the US and many across the world. And over here we bring everything from income to employment to poverty levels to health conditions to equity to education to demographics and you can drill down into one of these things like the environment. Please, internet gods, work for me. There we go. Lifetime cancer risk. And you can see over here something like the lifetime cancer risk across counties in the US. And you can go and, like, Louisiana is a really bad place to live. And then you can go in the timeline and see when they made certain policy decisions to allow petrochemical refineries. And you can see the spikes there, right? This kind of analysis shouldn't take a ProPublica reporter 6 months. It should be doable in a term project, in a lab, in a class by a student. And that's the goal over here. There's dashboards, as I mentioned. There's a whole bunch of other stuff here that I won't get into. But let me get into the heart of today's talk, which is sustainability. At the core of sustainability is, look, climate change is happening. It's not as simple as 1.5 degrees versus 2 degrees. There's a lot of similarities between IPCC data and NASA's Landsat data. Yes, IPCC data is open. Go ahead, download the 70,000 to 100,000 NetCDF files, which give you the different models. Well, some of them are on a rectangular grid, some of them are on an angular grid, and they'll give you projection runs and so on. A simple question like, how hot might it get in the next 10 years is actually quite complex. And Aditi has been helping us actually figure out how to answer that question. So I will let her go for it.
Okay, thanks everyone for having me. I'm hopefully going to get to basically this question in the next several minutes. Here's a little bit of introduction to begin with. So what global climate models do is that they break up the Earth into these little grid boxes that you see on my slide, and they track the flow of both energy and materials through that grid box. So they're hugely complex. So developing one of these climate models involves hundreds of people, typically in a national lab, and they need to come up with mathematical equations that represent physical processes that set climate. And each of these equations is then just solved repeatedly over and over again using supercomputers. And it generates, as you can imagine, an immense amount of data. Climate prediction is a little bit different than talking about the weather. So if I were to ask the question, how hot is it going to be on June 1st, 2045, that is a completely meaningless question because no one can answer it. However, climate models can help you say something about the statistics of weather in different climates or in a changing climate. So we can tell you something meaningful about what early June, 20 years from now, is likely to look like. So climate model projections help us estimate things like averages and extremes in a changing climate. There are over 100 contributing climate model groups, which all contribute to this thing called the IPCC assessment report. And this is referred to as the Coupled Model Intercomparison Project, or CMIP. This Google map, of course, on the left, shows you the geographic distribution of where these different models are coming from. There's over 100 of them. And you can imagine that the emphasis would be on different regions or different processes depending on where these labs are located. For instance, if you're in Southeast Asia, you presumably care quite a bit about the monsoon. Or if you're in high latitudes in Europe, you care quite a bit about changing polar climate, melting sea ice, things like that. And each of these models makes different physical assumptions in setting up these equations, and so each of these models is a little bit different. So what you end up with each of these model runs is a range of projections. It's not just one projection. And so it's incredibly complicated data and a lot of data. Each of these models, additionally, is run along several sort of storylines, if you will, about the future, which is what I'm showing you on the right. So these are assumptions, a whole set of assumptions about how, for instance, land use will change, or population will grow, and economies and emissions will change. So what I'm showing you on the right specifically is assumptions made about CO2 emission over the last two CMIPs. So these are CMIP 5 and CMIP 6, ranging from sort of very conservative estimates as to how much we're going to keep increasing CO2 emissions to rather more drastic CO2 emission scenarios peaking at various times in the future. So each of these national labs will run their models in a whole range of these scenarios and generate lots and lots and lots and lots of data, which to get hold of, a graduate student might end up spending weeks to months just downloading the data and then doing the analysis on it and visualizing it. The hope is that Data Commons will put all of this huge data set in one place, make it easily available, hopefully easily computable to work with, and also easy to visualize. The other thing with these global climate models is that their grid boxes are typically 100 by 100 kilometers. So it really doesn't know the difference between Palo Alto or Menlo Park or Mountain View or any of those things. So if what you really want to know is how hot is it likely to get in Palo Alto on campus 20 years from now so that we can plan for electricity demand or something like that, then this 100 by 100 kilometer grid box isn't really what you're after. So this is where something called downscaling comes in. So what downscaling does is that it uses the output from these climate models run for a time where observations exist. So for instance, what I'm showing you here is a period 2000 to 2010. And this has already happened. So a downscaling product will use local observations to interpolate statistically and actually give you a higher resolution grid than the model can. Similar procedures can be applied to climate projections going into the future. And this is what is typically known as a downscale product. In our collaboration with Guha's team, we focused pretty much on this NASA downscaling product, which has picked 35 out of the 100 or so CMIP models under 4 pretty common scenarios. So just to show you that this downscale product is actually doing something sensible, what I'm showing you here is a histogram. So just how frequently does something happen of daily maximum temperatures in Kern County. So Kern County is a little bit south of here. It's toward the south end of the Central Valley, and its economy depends quite a bit on agriculture. For instance, I read that Kern County produces 80% of the US's carrots for some reason. So in the gray histogram at the back is this downscale product of daily maximum temperature from Kern County. And these dots that you're looking at is the actual observations. So this downscale product isn't doing a terrible job at getting the variability of maximum temperatures in a decade that's already occurred. So now let's go into the future. What I'm showing you here is a future decade, so 2030 to 40. The histogram, as before, is an ensemble of models from this NASA downscale product. From a number of CMIP models. So this is average across all of these models, but you can also look at any individual model if you'd like. The red is a fit of a probability distribution function that is derived from several Gaussians. And let's focus in on these lines for a little bit. So let's look at this one to begin with. What this is telling us is that there is a 5% chance that 1 week in this decade is going to cross 45 degrees Celsius in Kern County. So these are a specific set of choices that we've made to produce this plot. But then Guha's team has developed a really nice Python notebook, which you can go into online. You can pick the county that you're interested in. You can pick the decade you're interested in. You can pick your variable. You can pick your thresholds. And you can actually use this now publicly available tool to answer this somewhat complicated question. How likely is it going to be that the temperature will exceed a certain threshold in a certain county in the US? Here's a little bit more detail on that. So we're going to stay with Kern County. And what I'm showing you on top is daily maximum temperatures, the probability distribution functions that we've developed. At the bottom is the daily minimum temperature, going from these nice light blue colors for the 1980s on the left to the really dark red colors for the 2040s all the way on the right. And just from a scientific perspective, it's interesting that the shape of these distributions really isn't changing all that much, but the daily maximum and the daily minimum temperatures are sort of incrementally shifting a little bit to the right, as you can see on the curve. So I encourage you to go online and check out this nice Python notebook. You can pick whatever combinations of weeks and years and locations that you like. And so the computation has been done for you. You can use these plots to learn whatever you like about temperature distributions. Just to switch gears a little bit before I end, I thought I would also show you a snapshot of some purely research data that my group has been working on, which we are using the Stanford Data Commons to make available both to collaborators as well as publicly. So this is a bunch of balloon data from a project which actually came out of Google called Loon. This is what these balloons look like. And here's the geographical distribution of where they've been. This is a really unique and novel data set. This is scientifically incredibly valuable. Take my word for it. And we are using high-resolution GPS measurements from these balloons to infer motions of air in the upper atmosphere, specifically about a certain kind of wave in the upper atmosphere. So what I'm showing you here at the bottom is some of these balloon tracks over pretty close to Antarctica, where there isn't very much data thus far. And these are these balloon tracks color-coded by the winds that they're measuring. And they're measuring them every 60 seconds, which is incredibly high resolution. So my group is working on putting up this data as well as a bunch of other data that we produce to make easily accessible to our collaborators as well as the public. So I'm happy to talk more about any of this stuff if you come find me or my research group, which is somewhere over there at the end of this. But thanks for your attention.
Thanks, Aditi. One of the high points of last week was Jahangir and Prashant and Aditi were iterating on these, how do you model these probabilities with this data, and does this seem reasonable, that seem in error bars and all of that stuff. And at some point, Aditi said, wow, and we did this all in about 2-3 days, and she said, it would have taken my students months to do this, because that's what the point is. So the second part of my talk, I'm going to talk about which communities are going to be affected and how, and more importantly, what can we do about them. And I'm going to take you through a couple of examples of work that our partners have done. I'm going to intentionally focus more on what our partners have been doing on top of this platform. So RFF, Resources for the Future, is an NGO based in DC. It's more than 50 years old. They do a lot of stuff. Now they've switched to sustainability and climate change. Hannah Druckenmüller over there and others have set up an RFF Data Commons you could go to at datacommons.rff.org. Their focus is on heat waves and other such things. It turns out that the number of heat waves that are being experienced on a yearly basis has gone up quite dramatically. And they look at, to step back, every community has certain vulnerabilities. The kind of vulnerabilities that a retirement community in Florida has is going to be different from the vulnerabilities that some community in Kern County or in your county has, is different from the ones that some counties in South Dakota have. And we have to understand some of these vulnerabilities are going to be made worse by climate change. And we have to understand which communities are at what kind of risk. So over here, they took the heat wave data, which they put into Data Commons, and started correlating it with a bunch of other things which are already in Data Commons. And just show you a couple of examples. The bottom left is the number of the x-axis in both cases is the number of heat waves. On the left-hand side, the y-axis is the median income. You don't want to be in the bottom right corner. We find a bunch of counties there. The dot size represents the population. The right-hand side one is x-axis is, again, a number of heat waves. Y-axis is cardiac illness, which becomes much worse as temperatures go up. You don't want to be in the top right. These can be used to identify vulnerabilities, and it becomes especially alarming when the same county starts repeatedly appearing in the wrong quadrant. And we see that with Starr County in Texas, and Hidalgo County in Texas, and some counties in Florida. It's not just the US, and this is some work that we did a year or two ago with Arun, back when he had some time to breathe. And here, we built models of wet bulb temperature. Wet bulb temperature, as you know, is a temperature at 100% relative humidity. We can't survive at a wet bulb temperature of more than 35 degrees centigrade. But even at 31, 32, life becomes really, really hard. These are all the places where over the next 10 years, over a period of 5 hours or more in a single day, these particular thresholds are likely to be crossed. And if you notice, South Asia isn't doing too well. And it's scary, not just because of how red-black it is, but also because of the population density. One of the first data commons to come up was the one at IIT Madras. And with them, we've been focusing on who are the people who we need to be helped most. And it's not just the obvious variables like the homeless population that matter. It's even sort of stray variables, like the percentage of schools with functioning toilets, which unfortunately in India is not 100%, because these are very good indicators of the ability of the local organizations to support themselves. In talking about South Asia, the Indus, Ganges, and Brahmaputra, the three of the big rivers in the region, they together feed about 1 billion people, a little bit more than that actually. These are fairly perennial rivers, meaning their flow rate doesn't change too much through the year, because of those black dots, which are the big glaciers that hold the water. Now, if things don't go too well, sometime in the 2050, 2060 range, the thresholds, the temperature at those glaciers is going to cross thresholds, and these glaciers will not hold that much water anymore. at which point in time, these rivers will start behaving much more like the Nile. The amount of human misery that's going to cross has never been seen before. We can prepare for it. Of course, if we can make sure that doesn't happen, that's good, but even otherwise, by building reservoirs and so on and so forth. This is going to be one of the biggest building projects ever undertaken. And we got to start now. And we're working with the IITs and others to get the ball rolling on understanding what might possibly happen. Coming back to the US, I spoke about Feeding America. Thanks to Emily Ma at Google and Mark Mollenkoff at Feeding America, they have set up a Feeding America Data Commons. You can go to datacommons.feedingamerica.org, and somewhere here I have this. This is the India Data Commons. I must have a window open here somewhere. This is the Feeding America Data Commons. And they were asking about cardiac health and food insecurity. I'm going to be a little adventurous. Okay. Come on. Come on, internet gods. Yeah, there we go. That's a correlation between cardiac health and food insecurity in this country. Each dot there is a county. It's really, really scary. If you look at the dots over here, this is Todd County in South Dakota. This is Oglala County, again in South Dakota. You want to drill down and see what is happening over there. Maybe asking too much of my internet connection, but you get the basic idea. And what's interesting, yeah, there we go. Everything about this place so that you can understand what's really happening. Imagine you were a county official over there. This is something that you start with. There's food, I mentioned food insecurity in California. What's interesting over here is the variables in the red box, that's all is coming from Feeding America. The rest comes from Data Commons, and they get it for free without replicating it. These are the dots. These dots, each dot here is a California county, and you can see that the counties that are most at risk are ironically the agricultural counties. So a big question is, we can go on and on. We've all read articles about how different communities are at risk in different sorts. At some point, the question comes, so what are you going to do about it? And for that, we are partnering with TechSoup, Marnie Webb, Steve Lee, and Ken from TechSoup, who's here. TechSoup is an NGO that which does work with, which helps other NGOs with their tech needs. They partner with a wide range of, these are the IRS-registered nonprofits of different sorts across California, and they seem to be working with over a quarter of them. So let me back to what we are doing in a specific context. So going back to the food insecurity in California. So in Kern, these are the most food insecure counties. And I'm going to pick on Kern County because it's a big county, unlike some of these others. Its population is almost as much as Santa Clara County. It's the salad basket of this country. 13% of the people there are food insecure. It's actually much worse than that. If you drill down, and you have to, all of these data is from Data Commons, you need to go look at the particular census tracts. And there's a census tract at the top of Kern County over here. 12% have heart disease. Median income is $24,000 a year at a family level. 25% are below the poverty line. It's a really old community. 58.5 is the median age. Less than 10% are college educated. When the temperatures go up, these communities are going to be severely affected. And no number of papers that we write and dashboards we create is going to help them. So we need to work with the entities, the organizations that are on the ground there, and we can't reach thousands of these organizations, but we're working with TechSoup and Feeding America to others. So for example, in the case of this census tract over here, there's three, these little black dots are USDA summer meal sites, community service organizations, and so on. There's this little black dot here. Canyon Hills of Kern River Church. This bottom thing, that's them. And that's the pastor there. He can't help that big region by himself, and we need to help him, and we need to give everything we can, and that's the goal here. I'm so glad to be working with Stanford because this is the goal of the accelerator too. Let me switch. Extreme weather events. These are the ones that get a lot of attention. Dashboards bring a lot of focus. During COVID times, we were all focused on the Johns Hopkins dashboard because they told us what was happening. Arising out of a conversation with Arun, we've been building together with some of the Stanford folks a disaster dashboard. And let me actually see. Nope. Okay, this is going to be incredibly ambitious, but if it works, I'm actually going to datacommons.stanford.edu, and you can go underneath there. The likelihood of this working is not very high. It worked. That was a miracle. These are the fires, floods, wet bulb excesses, droughts, storms, etc., across the last 12 months across the globe. And you can go change all kinds of settings and do all kinds of things, drill down, go into a particular fire, get the details. And this is an incredible collection of information from the US government, from MODIS satellites, from analysis of various satellite imagery, and so on and so forth. And the same approach that is being used over here is going to be extended to do things like get a good inventory of all the places where people are claiming carbon credits from and things like that. On the topic of extreme events, I'm going to give it to Ram, who's going to talk about the impact of extreme events on power.
Thank you for having me. So one of the applications we built on top of Data Commons and on the dashboard, on top of the dashboard you saw, was to try to answer the question, we have all heard extreme events seems to be causing lots of power outages, but is that actually true? So to do that, the first step was to decide how do we track these outages, and so we use the average number of minutes per customer where they are without power in a year. That's called SAIDI. So we built and collected the most comprehensive SAIDI data set for the US. It covers 39,000 zip codes and nearly 100% of the US population. And to collect this data, we went from data that's available in the web all the way to like books that were scanned and drawn from libraries in San Francisco, Texas, and all over. And we have made this data available in the Stanford Data Commons. This is the largest record in existence right now of this information. We then built these extreme weather indicators on top of the weather data that Aditi and Guha talked about. And here's kind of one example of this indicator of extreme cold shown on 2021. And you can see that dark blue are the places where you had a high intensity of extreme weather. And you can see Texas is pretty dark blue, and this was the year of the so-called Texas freeze. So one question was, well, what happens to the electricity reliability, to SAIDI, during the freeze? Here's what happened. So 4.5 million customers without power for 2,000 plus minutes. And you can see the whole of Texas extremely dark red, very, very high SAIDI. And we look at our indicators, and you can see that extreme snowfall, extreme cold were high as well. And so the question was the extreme cold actually causing this high SAIDI? And when you look through history, you find there were similar extreme moments. But as you can see, the SAIDI was not very high. And so there was no extreme outage. So what was actually happening? So Tao, our student, he actually figured this out, that in fact, the issue with extreme weather and infrastructure is that we can handle one extreme event. But when they compound, when they happen together, when you have extreme cold, extreme snow, or extreme cold, freezing rain together, then it's something really unprecedented, and it impacts the system. And you can see here our compound event is very unique. Nothing like this had ever happened before. So using this insight, we were able to create predictive models that allow you to estimate different types of investments on every county in the United States to respond to these extreme events. I just want to show you one such example. For example, we wanted to understand how much increase in reliability can you get from undergrounding power lines on every county in the country. No single utility, no single county, no single state can do this data, because you need to see the variation of all of these extremes, and they're only happening over the whole country. And you need a long period of time of data. Here you can see the curve of SAIDI versus the undergrounding rate predicted for Miami-Dade. And you can see in blue the current rate of undergrounding. So they have about 30% or 0.3 undergrounding of their lines. If they increased it just slightly, they would have an enormous benefit and increase the reliability by reducing their SAIDI from something like 5,000 minutes to about 2,000 minutes per customer per year. That's a lot of savings. Here's Queens. That's an example where investments in undergrounding don't make a lot of sense. You're already in a place where you don't benefit from it too much. So the last thing I want to share with you is that you heard Guha talk about the inequity, and we were really curious about, well, how is the situation with electricity reliability? So normally this would have been very challenging to do. You have to go and collect these other data sources, but we had the Google Data Commons, and we had our data on the Stanford Data Commons, so we combined both, and we can do plots like this. This is the trend of SAIDI, and of course lower is better, with income. And you can see that low-income populations have 33% more outage minutes experienced than higher-income populations in the United States. You can measure vulnerability through the Social Vulnerability Index from CDC, very similar observation. And how about food insecurity? So the more food insecure you are, the more minutes of outage you experience. And when you have an outage, of course, your food goes bad and so on. So we are now working on putting all of this data in the Stanford Data Commons and making these scripts available. But one of the things that I wanted to highlight is these models we've built can have a real impact because you can actually decide on policies based on it. And the second thing is normally when we did projects of this type, 80 to 90% of the students' time is dedicated to cleaning the data, aggregating the data. So typically your PhD is 4 years of getting stuff, and maybe 1 year or 6 months of analyzing, and 6 months of defending, writing the thesis, and getting everybody to sign off. And now with the data commons, I think we can invert that. We can do 20% of the time is getting some new data set, and then using the power here to really look across. Thank you very much.
Thank you, Ram. It takes only 6 months to get the thesis signed off. Took me a bit longer. I was going to talk about education, and if people are interested, come talk to me. The one fascinating thing I'll leave you with is, based on this, we're building a curriculum of data literacy is most important, and everybody should know data literacy, even if you're a humanities major, even if you don't know programming. And one of the things that we've been building is a data literacy for non-programmers course. And we are actually hoping to, we're working together with Spelman University, and we're hoping to pilot that with a bunch of HBCUs later this fall. Every community college, every student should have basic data literacy. They need to understand what a sample means, what bias means, and so on. If you're interested, come talk to me. I'm actually going to skip the part on health to, I'm being told we're way out of time. I'm just going to give one example. Right at the beginning, I said, just ask in natural language, right? It's a big promise. So I will see if I can show you. This is a system which has not been released, so it's, you want to just ask, what are the projected temperature extremes across California? And we use language models, but we use them only for understanding the query, not for answering. The answers come from data commons with provenance and so on and so forth. So there is no issue of hallucination, falsification, making up data, and things like that. And you can see there are places in Inyo County, Monyo County, et cetera, that are going to get really hot. We're talking about Kern County. Tell me more about Kern County. Come on. Please. Yeah, there we go. What are the most common jobs there? As Aditi mentioned, the most common job is agriculture, forestry, fishing. Which jobs have grown the most? Which is a different story. Because you see, the jobs that have grown the most are in healthcare. Wonder what the most common health issues there. The most common health issues are issues of age, blood pressure, cholesterol, arthritis. Which counties in California have the highest levels of blood pressure? Kern County, Tulare County, Merced County. Wonder what it is across the US. Which counties in the US have the highest levels of blood pressure? It's actually doing all this in real time, so that's why it's a wee bit slow. As we know, the southeast of this country, Mississippi, Alabama, Louisiana, are not the healthiest, and it shows. How does this correlate with income? There. Should be able to be pulling data from a bunch of different things, just ask for it and you get it with provenance, et cetera, et cetera. That's where we're headed to. And when Stanford puts up its data or other data from elsewhere on Data Commons, there's a bit of work involved, but all of that data will be accessible, not just to the students, but anybody, anywhere in natural language. So with that, thank you all. And
so I have questions for the panel, but I'm sure you do too, so let's go to the floor. Questions for any of the three? Yes, far back on the right. Nope, sorry, you in the blue shirt with the sunglasses right here. And then,
how are data sets selected? Who selects them? Who ingests them?
so there's actually two questions there. The organization which is hosting that Data Commons, right, does the whole thing. They select which data sets, and they are responsible for the cleaning and adding them and so on. In the case of Google, we've picked broad topics. There's one class of topics that came from the kind of questions that Google users were asking on Google search. Around sustainability, our focus has been around food, health, shelter. Let's make sure those are answered. Stanford, each faculty will have their own priorities and so on. At the schema level and API level, we try and coordinate across schema.org and a bunch of other standards entities in order to develop the common schemas.
just in front, yes, right there. Mike's coming.
Is there a way to incorporate data from local studies that aren't global or national?
Yeah, absolutely. It doesn't, I mean, you could put in, a lot of the data that is over here is as local as, for example, we have childhood asthma rates, which is available only really in California and a couple of other places. There's some other work that incorporates data which is as local as a city. And you can add that in your own private layer. So one of the important things that I didn't mention is that when you set up your own data commons, you don't need to make it publicly available. It could be just your private data commons because you've not yet published the data or for whatever other reason. It could be private patient data. And it can still draw on all the data from the public data commons, which is especially important in medical contexts.
Thank you so much. This is super exciting, and I'm just so moved that you're visualizing data and making it accessible to make like real changes. My question is, how do you guard this incredibly powerful tool against misinformation and misinterpretation of data?
Oh boy, I was really afraid somebody was going to ask that. But it's a fantastic question. Unfortunately, there is no guarantee. There is no guarantee of misuse when you make any useful tool available. The important thing is that we need to build, the different data commons need to build trust by the quality of the stories they tell and by the other things they do. And hopefully an RFF or a Stanford will be, and a Feeding America, a TechSoup will end up being a lot more trustworthy than some other organizations. I won't mention them, right? And then it just comes by providing the highest quality of data and by transparency, allowing anybody to, when Aditi showed the temperature data, you could go to the Data Commons site and go look into the Python notebook, look at the assumptions that were made, and be able to drill down.
Have there been any data sets that you really wish that you had that you couldn't get because of the terms of use? And is Google doing much legal support around data use agreements?
There are a whole bunch of data sets which I wish I could incorporate, which I can't because they're only available for non-commercial purposes, and Google is a commercial entity. I can give you an example. The Stanford Graduate School of Education has a fantastic data set around elementary and middle school achievement, the CEDA and SEPA data sets, right? I am urging Arun and co. to add that to Stanford's data commons because Stanford is not a for-profit entity. So there's a bunch of other data sets which could be, there's a ton of them at CDC which are in PDFs, which we know there's actually relational databases behind them. So there's a ton of data, especially in government organizations and others. And then there's a whole license issue too. And
John?
Is the data commons used in China? Does China contribute to it, benefit from it?
Data Commons runs on GCP, which, as you know, is not accessible in China. However, one of the people on my project, Wei, I don't know if he's here, who's been been with us for 5 years, is going back to China in the fall to be a faculty at the University of Science and Technology. And one of the things they are interested in doing, it turns out they've been following this and they're really fascinated by it. And they're trying to create, the plan is tentatively to create their data commons, which is, to me, fantastic. Does that answer your question?
So the answer is no, not yet.
No, not yet, but at some point in the not too distant future, the code is all on GitHub, so they just get started with it. They'll probably host it on Alibaba or Azure or something like that, and then bring it up. And then, we have a data commons that Snowflake has up, and so it's been done before, so they should have it. I do hope the schemas don't get forked, and I hope we can make it so that the data is easily joinable. But these are things which. But look, at the end of the day, they're producing a lot of CO2.
Oh.
I would like to be able to. Sorry.
No, it's good. Sorry, that wasn't a signal. That was, okay, Jamshid, and then I will ask a couple of questions of Aditi. And
So the data is good about the past. What about the future? How are you going to use it for predicting?
Yeah, so all the IPCC data is future. We are also working with a bunch of people, Gary King from Harvard and others. So for simple things like population, there's various prediction measures, but I'd like to be able to predict things like the rate of cardiac health, asthma, all kinds of fertility, all kinds of other things. And we are trying to do, rather than build models on a per variable basis, if we can just do it across the board, that would be fantastic. There's also far out exercises that our groups are starting off saying, can we build the analog of a large language model on top of all this data, taking it as a sequence? It is going to be fascinating. I have no guarantees about what comes out of that, but it's going to be fascinating.
So before we close, I want to talk a little bit about the possible applications of this capability within the mission of the school. And so maybe first, Aditi, about what opportunities you see for bringing this into pedagogy and to research, and then maybe a bit, Ram, on impact.
Okay, on the teaching front, I teach a couple of undergraduate classes involving the scientific basis of climate change, which appear to be becoming a bit more popular with every year that I teach them. So I do things like showing them outputs from climate models in order to make sort of physical links between what makes sense and what the climate models are actually doing, which also feeds into the last question a little bit. We would like future predictions to be physically consistent. So yeah, I'm really hoping that I can leverage this tool to show visualizations of large-scale climate changes to my undergrads in a way that is visually appealing and does not involve dry math. On the collaboration front, at the moment, I lead a team of about 30 or 35 people with 8 teams across the US and Europe. And one of the current challenges has been sharing some very high resolution data that we are generating across the teams. So something like this would help us with that. I mean, it doesn't necessarily have to be publicly available instantly, but then derived statistics and implications could be publicly available while we share data amongst collaborators. So I'm optimistic on both fronts.
Great. So Ram, you were talking yesterday about the work you've been done on solar penetration and how this might help that effort. Tell us about that.
Yeah, so we have done a lot of work to map the global renewable energy infrastructure, both the centralized and distributed. Only about 50% of it is known, where it is and how it's deployed. And we have done it for the United States. We collaborated with partners in Europe and did it for Germany. And now we are working with students here and some collaborators to try to map in Africa as well. And one of the things that we have been learning through this exercise is that showing how things can be done or a model can be done to the US and used by our decision makers here or by renewable energy providers here to optimize their offerings and how they deploy these technologies is great. But if you want to have impact, you have to really go out to the rest of the world. And how do you do that? Well, one is you need data, but two, you also need the people who can actually do these models with their local realities, with the decisions that need to be made there. And those same people, after going through this process, they will end up being the decision makers in the future. So you need to create the ecosystem of people around this. And we find that Data Commons can really serve as an interface for that, because we can very easily pass on the ideas, the models that we build, and they can put their own data commons together, and through that effort, really create an ecosystem and educate themselves on how to do this. This is extremely impactful. It's huge. I was just thinking the other day, I'm originally from Brazil, and Brazil has a ton of data by law that it has to collect. But all of this has been siloed in different places, and talking to colleagues there, and I just showed this analysis on Sadie that you saw, and they were floored, and they said, wow, we really need to do this for so many things out here, and it will really help us decision makers and companies and so on to focus on critical issues. But you need the people to do that.
Great. So we are up against time, so we're going to have to draw a line there, but I hope this gives you a sense of the exciting potential that's been created here and the work that Guha and a growing number of faculty here are going to be able to do together going forward. So join me in thanking the panel for this presentation and for joining us.